Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about speed of sound, Mach number, and flight regimes. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Speed of sound. Air is a gas, and one of the most important properties of any gas is the speed at which sound travels through it. When we talk about the speed of sound, what we are really describing is the speed at which a very small disturbance moves through the medium. Sound itself, as humans experience it, is not just this physical disturbance. Rather, it is the perception created in the brain when the inner ear responds to pressure variations in the air. So, while sound is a sensation, the speed of sound refers to the physical transmission of pressure disturbances, independent of whether or not anyone hears them. The speed of sound in a gas is directly related to the temperature of that gas, and more precisely, it depends on the square root of the absolute temperature. This relationship is captured by the equation. Speed of sound equals the square root of gamma multiplied by the gas constant multiplied by the absolute temperature. Where A is the speed of sound, gamma is the ratio of specific heats of the gas, R is the specific gas constant, and T is the absolute temperature. Sound travels faster in hotter gases, because higher temperature means the molecules have more energy and can transmit disturbances more quickly. It is important that the temperature is measured on an absolute scale, such as Kelvin or Rankine. Since temperature in the atmosphere changes with altitude in a complicated way, the speed of sound also changes as you go higher or lower. To account for this, engineers have built standard models of the atmosphere that predict how temperature varies with height, allowing the speed of sound at different altitudes to be calculated. As an object moves through the air molecules near the object are disturbed and move around it. If the object passes at a low speed, typically less than about 200 miles per hour, the density of the air remains nearly constant, and the flow is considered incompressible. However, at higher speeds, some of the energy of the object goes into compressing the air, which locally changes its density. This compressibility effect alters the forces acting on the object and becomes increasingly important as the speed rises. Near and beyond the speed of sound, which is approximately 330 meters per second, or 700 miles per hour at sea level, the compression waves merge into strong shock waves that affect both lift and drag. Because the effects of compressibility are closely tied to the speed of an object relative to the speed of sound. Aerodynamicists use a special parameter called the Mach number, named after Ernst Mach, a late 19th century physicist who studied gas dynamics. The Mach number is defined as the ratio of the velocity of the object to the local speed of sound. Mach number equals the velocity of the object divided by the local speed of sound. Where m is the Mach number, v is the speed of the object, and a is the local speed of sound. In words, the Mach number is the object's speed divided by the speed at which disturbances move through the air around it. Mach number. Flight conditions can be categorized according to Mach number as follows. 1. Subsonic. Subsonic conditions occur when the Mach number is less than 1. At these low speeds, typically below about 200 miles per hour, compressibility effects are minimal and can often be ignored. The density of air remains essentially constant, and flow behaves almost incompressibly. 2. Transonic. As the object's speed approaches the speed of sound, the Mach number nears 1, and the flow is said to be transonic. At exactly Mach 1, the flow is sonic. Compressibility effects become very significant, leading to phenomena such as flow choking and increases in drag. Early pilots referred to this increase in drag as the sound barrier, though it is not a physical barrier but a result of transonic compressibility effects. 3. Supersonic. When the Mach number exceeds 1, the flow is supersonic. For example, a Mach 3 aircraft flies 3 times faster than the local speed of sound. In supersonic flow, compressibility effects are strong, and shock waves are generated along the surface of the object, affecting lift and drag. 4. Hypersonic. At speeds much higher than the speed of sound, typically above Mach 5, the flow is considered hypersonic. At these extreme speeds, some of the object's energy goes into exciting the chemical bonds of nitrogen and oxygen molecules in the air. Therefore, the thermochemistry of the gas must be considered when calculating forces, because chemical reactions can occur due to the high energy involved. Since the Mach number depends on the local speed of sound, and the speed of sound depends on air temperature, which in turn varies with altitude, engineers and scientists use mathematical models of the atmosphere to predict how compressibility effects change at different heights. This allows accurate prediction of forces, lift, drag, and shock wave formation for aircraft traveling at various speeds and altitudes. In summary, the speed of sound determines how disturbances propagate through air, and the Mach number, which is the ratio of an object's speed to the local speed of sound, classifies flight regimes into subsonic, transonic, supersonic, and hypersonic. Understanding these concepts is essential for analyzing aerodynamic forces, predicting shock waves, and designing vehicles that operate efficiently at high speeds. Okay guys, now let's have a little quiz. The quiz consists of 3 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. The speed of sound in a gas depends primarily on which of the following properties? The correct answer is gas temperature and ratio of specific heats. Question 2. Which flight regime is characterized by Mach numbers greater than 5, where chemical energy in the air molecules may become significant? The correct answer is hypersonic. Question 3. What is the Mach number a measure of? The correct answer is the ratio of the object's speed to the local speed of sound. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures. where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about shock waves, normal and oblique. See you in the next video. Bye.